Welcome back. So a little update about this mysterious meme that I shared with you all yesterday. This was I follow this Twitter account that posts math memes, and anyone have any more thoughts? Were you thinking all night about this the same way that I was? I talked to two other of the math professors here and asked them what their interpretation was. I replied to the tweet. I never really tweet anything. Like, I read other people's, but I don't say much. I just I sort of advertise my YouTube videos, but I have like 20 followers or something, so it's irrelevant. Anyway, I said, I don't get it. What does this mean? That's me right there. And they said, this is a somewhat condescending reply. They explained to me what an integral is, which I know that. So I said, yes, I know what these things are. And this is actually what two other professors I showed them to. This was their guess. Their guess was that YouTube plays the videos real nice and smooth. Sorry, the ads. The ads are real nice and smooth, but when you get to the actual video, it's all like messed up and choppy. And that, I believe, is what this is supposed to mean. That the smooth one is when the ad is playing, which is like the real function, and the video itself is all chopped up like a Riemann sum. And this is what the people seem to indicate. They said, yes, correct. Yeah. I got 19 likes on that may be my personal record for likes on a tweet. So I guess, I don't know, is this like a thing that people know about YouTube? This never occurred to me, this fact about YouTube plays the ads better than the videos. I don't know. I actually have a subscription to YouTube Premium, so I don't see the ads. It's because my sister got one for her family, but she had I guess a family subscription is 6 users, so she gave me one. Thanks, Emily. All right. This is the end of my story about that meme. You missed it. You'll have to ask them. We figured out what the meme means about the sum and the integral sign. I'm sure you've been thinking all night about it.
What was the meaning?
I'm not going to tell you now. You have to ask them. Watch the recording of class afterwards. All right, so we're talking about power series. Oh. Okay, we're talking about the power series. Yes, I have the checklist for the old ones going around, so make sure you get it. Power series. So what we've been talking about so far have been power series that look, something like the sum, I don't know, I'm just going to make this up, x to the n over 3 to the power n. We talked about that particular example last time. And power series are like this, and they have certain x for which it converges and certain x for which it diverges. And we did a couple examples at the end last time about how to find for which x does it converge. And the way to do that is basically you use the ratio test, although you can use the other test, but the ratio test typically is the most convenient to use to answer this particular question. For which x does it converge? All right. Now, all of the examples that we did last time were actually a special type of power series. And this is an example of one like that. This is called a power series centered at 0. 0, that's the number 0. Centered at 0. And you can also have a power series centered at something else. So that's what I want to talk about at least a little bit today. And you do more or less the same stuff with these power series centered at some other numbers. But let's talk about that. So you can center your power series around any real number. If you use 0, it becomes sort of simpler looking. but we can also do this for other numbers. So I'm going to say for any real number A is going to be the center of my power series. A power series centered at A power series centered at A is something that looks like this. It looks like the ordinary power series, but instead of just powers of x, it looks like, some coefficient and then some coefficient on x minus a, and then some coefficient on x minus a squared, some coefficient x minus a cubed. So again, it's like an infinite polynomial, but the individual terms, instead of just a power of x, it's a power of x minus a. All right, and this is called a power series centered at a, and of course this you can write with the summation sign. I suppose I started at 0 there, so this would be a sum n equals 0 to infinity cn x minus a to the n. Did everybody get my list here? Anybody still need to tell me about old ones? Send it back behind you after. Okay, this is a power series centered at A, and I hope you agree, if I decide to do centered at 0, if I use 0 for this number A, then it just looks like one of these ordinary power series where it was just powers of x every time. But you can, instead of doing centered at 0, you can do centered at some other value. All right, and there actually is a reason why you would want to consider series like this, but we'll get to that later. Let's just talk about how can we find where it converges. It's actually the exact same process. Let's just try an example. So here is a power series. This one is a series centered at 2. How about this? All right, this is centered at 2. All right, it's always what you want to see in your power series is always x minus something, and the center is the thing which is being subtracted. So this is not centered at -2, it's centered at 2, even though it's subtracted. Everybody get the list now? Okay. Centered at 2. All right, but anyway, I would like to ask the same kinds of things we were doing at the end last time. For which x does it converge? All right, and just like before, we are going to use the ratio test, and there really is no special tricks to this. It works out almost exactly as before. The very last part looks slightly different, but it's really nothing fancy. So I'm going to do the ratio test. All done? All right. Now everybody got it for reals? Okay. We're going to do the ratio test. So that's this L thing is lim n goes to infinity, absolute value, and I go an plus 1 divided by an, and I want to, I'm going to write that as sort of reciprocals. So an plus 1 is using n plus 1 instead of n, so this will say n plus 1 plus 4. And then times the reciprocal of an will look like n plus 4 over x minus 2 to the n. All right? And then we're going to simplify as much as we can here, which typically involves like grouping together similar terms and canceling a bunch of stuff. As for x minus 2, you should never try to expand that in these ones with series centered at something other. Just leave x minus 2 together, and it will nicely cancel with the other x minus 2's. I believe the cancellation will result in just a single factor of x minus 2, right? We had n plus 1 in the numerator and n on the bottom, so they cancel, leaving 1 remaining in the numerator. And then the other part looks like this fraction, n plus 4 over n plus 5. And when I take the limit as n goes to infinity, that fraction part becomes 1, because it is a ratio of polynomials having the same coefficients, or the same degrees. The coefficients are 1 both times. So this, in the limit, that becomes 1, and I just end up with absolute value x minus 2. All right? When you take the limit, the x just stays like it is. The n thing goes to a 1. All right? And so when does it converge? It converges when the L is less than 1, right? So that would be absolute value x minus 2 less than 1. And this is pretty much exactly what we did at the end last time. Now, here's where something is, like, I suppose, very slightly different, i.e., I would like to write this as x between something something, right? This is how I usually like to write the answer at the end. Now, if it were, can we say how to work that out? Yeah?
Well, like, wouldn't you look at the x minus 2 and the absolute value is less than 1 and kind of treat the less than like an equal sign and solve for x? To like figure out what the x is supposed to be less than?
Maybe. You mean without the absolute values?
I mean, but would it not matter if the x is still be your absolute value at the end? I might not be making any sense.
Yeah. So one thing I'm not sure you're suggesting this, but one thing that is not allowed, you should not just sort of look at this and say add 2 on both sides and get absolute value x less than 3. Okay. Those are different because well, they just are. I would say, you know, the way that we would have handled this last time is you would end up with some answer. So this is like what they would look like at the end last time, maybe 4. I'm just making this up, and then that you turn into this. So when I have absolute value less than something, that's the same as this kind of double inequality with a negative and a positive, and x is in the middle, all right? So I'm going to try and think of this in that way, and maybe I'll do this in 2 steps. I will say absolute value x minus 2 is less than 1, which means I go 1 and minus 1 here, and then put x minus 2 in the middle. So this step here is exactly the same as this step. It's just I don't have just x, I have x minus 2. And now that the absolute values are gone, you can actually add 2 throughout this entire thing. So I'm going to add 2 everywhere, to all 3 parts. So it's kind of like I go plus 2, plus 2, plus 2, right? If you want to write them out that way. In any case, on the left I get 1 less than x less than 3. And that is the way that I like to write this. All right. I hope you should definitely believe me now that that is not the same as saying absolute value x less than 3. This is different. Okay. So anyway, it converges there. Converges for those x. There are also, and it diverges when x is outside of those. But we also have to, as a special case, check those 2 endpoints. You could think of that like an interval. It's all the numbers from 1 to 3. And we need to specifically, as special cases, check at 1 and 3. So it converges there, and it diverges when absolute value x minus 2 is greater than 1. But we need to check specially x equals 1 and also x equals 3 to see if it converges on those 2 specific values. And for those ones, you know, you do these specific checks by going back to the original thing and just replacing x by 1. So my original series was sum, I'll just write it this way, exactly as is, x minus 2 to the n over n plus 4. I'm going to plug in x equals 1 here. It will say now 1 minus 2 to the n over n plus 4. This is the sum, negative 1 to the n over n plus 4. Does that converge or don't? Does this look like anything to anybody?
Alternating?
It looks like the alternating harmonic series. It has n plus 4 on the bottom rather than just n, but that you should feel like doesn't really matter all that much. And does that converge or not? The alternating harmonic?
No.
That one does converge because of the alternation. That's the one that converges to the natural log of 2. Now this one doesn't converge to natural log of 2 because of this extra plus 4 down there. But this is, can I just say this is basically the same as minus 1 to the n over n, which converges. When I say basically the same, actually you can be very specific about it. This one like starts with -1 over 1, then -1, then +1 over 2, then -1 over 3. This one is the same. It starts with -1 over 5, and then goes to +1 over 6. So they are the same. It's just this one skips over the first 4 terms of that one. Anyway, if you want to be very specific about this, you would use another comparison test or something like that. You can, and it's not hard to do the details, but if you do the limit comparison, you will see that the convergence of this is the same as the convergence of this. And so that means this one converges. All right, if you wanted to include all the details, you would use the comparison test or something like that. All right, okay. And then, okay, that was x equal 1. What about the other endpoint was x equal 3? We should do that one also. So this time it looks like x minus 2 to the n over n plus 4. This is the sum. So when I plug in 3 minus 2 to the n over n plus 4. This is just 1 over n plus 4. This is the harmonic series, but not alternating, and that diverges. Right? Again, it's missing the first 3 terms, but that doesn't really matter at all, or the first 4, however you want to count it. This is like the sum 1 over n, not alternating, which diverges. Again, if you really wanted to prove that they are that this other one also diverges, you would use like the comparison test. All right. So, what's my final answer then? It converges. Remember what we said. I'm going to try and summarize. It converges here from 1 to 3, including 1, but not including 3. All right. So my final answer would be converges for 1 to 3, but including 1, but not including 3. This diverges otherwise. All right. That whole example was basically the same as one we did last time. All right, great. If you like to sort of visualize these things, you could think of this as sort of on your real number line. 1, 2, 3. This is the interval from 1 to 3, including the 1 but not including the 3. This we would typically draw something like this. Right, this interval here. The answer is that interval, which includes that one endpoint and not the other. It turns out when you do this, you actually always get an interval. And in this case, we say the interval of convergence. The interval of convergence is, I would write this interval like that. The interval from 1 to 3, including 1 but not including 3. All right? This is the interval of convergence. And there's another just sort of simple terminology that we're going to use about this. In this case, how far across is that interval? The width of the interval is 2. For technical reasons, it's more convenient to talk about the radius of the interval, halfway across. We call this the radius of convergence. Radius is a little strange to use about an interval, but this is the common term that's used. Convergence. The radius of convergence here is 1, and that's because the distance from the middle to the side of that interval is distance 1. The radius of convergence is distance 1. So what we get is an interval which has this certain radius of convergence. Anyone want to suggest now why such a series is called centered at 2? It has to do with this interval. It is not a coincidence that this is an interval which is centered at 2. So people talk about the radius of convergence because the interval of convergence is always an interval where the 2, in this case the 2 is in the center, and how wide is it? It's this wide. Radius of convergence is 1. All right. This is why this power series is called centered at 2. Because if you think of the power series as representing a function, it only makes sense to plug values in this region, because any values out here, the answer would be infinite. So the series kind of only exists, or it only makes sense in this little region here, and the center of that region is at 2. So we say the series is centered at 2. Anyway, I'm going to write this sort of collection of these facts in a big theorem. We don't need to prove this. I mean, it's just based on what I said over there. But it says if f of x is given by a power series centered at some number a, then there is a radius of convergence which I will write as a big R for now. For any power series centered at whatever, there always is a radius of convergence such that the series converges when absolute value x minus a less than r, and diverges when it is greater than r. The two endpoints, the special cases, actually they could go either way, and from example to example, it's not generally possible to predict what happens on either of the two endpoints, and so I'm just not going to say anything about those. The theorem just says there is always a radius of convergence, so that the thing converges when your x value is within this radius, and it diverges when the x value is outside of this radius. And I will just say it is possible, so possibly, this is like the worst case scenario, r equals 0. It can happen that the radius of convergence equals 0. And this means the series only converges right at the center point, but nowhere else. All right? So possibly r equals 0, and in this case, it converges only at the center point x equals a. This is kind of the worst case scenario if you want your series to be useful for calculating the values of the function. It means the series only works at that one specific point. And it's also possibly, r equals infinity. What that means, your interpretation of that is that the interval of convergence is just all of the real number line, right? This radius, how wide is the interval, is infinitely wide. So possibly r equals infinity, in which case it converges for all x. All right, and that is kind of like the best case scenario. It means that you can use this series to get answers for any values you like. All right, this is the theorem about the radius of convergence. All right, can we just try a couple more of these? Find the radius of convergence. So often the homework questions or whatever, sometimes they'll say find the interval of convergence, or sometimes they'll just say find the radius of convergence. And finding only the radius is, I suppose, a little bit easier, although they're pretty much the same. But finding the radius involves slightly fewer steps. So let's try one. Just find the radius of convergence. I got 2, and then I have 1 for you all to try. Well, these will go similarly as the ones from last time. 2 to the n, x to the n over root n. All right. As is my custom, I'm going to use the ratio test. So we do the ratio test. It looks like lim. So I'm going to go absolute value, of course, and then a n plus 1 looks like 2 to the n plus 1, x to the n plus 1 over root n plus 1. That's a n plus 1, and then divided by a n, in other words, times the reciprocal of a n would be root n over 2 to the n, x to the n. All right. Rearrange stuff here and cancel as much as you can. Somebody want to say, what about the 2's? What remains once I cancel 2's? I think just 2. Yeah, this is not a trick question. 2 to the n plus 1 up top, 2 to the n on the bottom. They all cancel except for just 1, 2 will be remaining in the numerator. So 2. X's, I think it's exactly the same with the X's. I have n plus 1 of the X's up top and n of the X's in the bottom, so they cancel, leaving just 1 X left over. And then n over n plus 1. So again, I will gather those together, and I'm going to do this to them to make it clear what the limit is going to be, right? By sort of absorbing them both into the same radical sign, that means that the limit will be 1 because it's the same degrees here and coefficients are the same, right? So doing the limit, I just get this absolute value 2x. And so to find the radius of convergence, we basically just say this is less than 1, and then try and kind of solve for absolute value x if you like. This would involve dividing 2 onto the other side. Absolute value x less than 1/2, and that's the radius of convergence. Well, I'll just write it. All right, and this one is centered at 0, so the interval of convergence is -0.5 to +0.5, although I don't know about the endpoints, you would have to check them specifically. But in this question, if your whole job was just to find the radius of convergence, and so you don't actually need to worry about checking the endpoints because they don't affect how wide the interval is. All right, 1/2 is the answer. Let's try one more. So that was centered at 0, which makes it a little easier to handle the algebra. Let's try one that's centered somewhere else. But there's really no super special tricks that you need. So how about x plus 3 to the n over 4 to the n. All right? This one is, so again, your job is find the radius of convergence, r. This one is centered at, what is it centered at? Huh? Yeah, -3, right? The centering business, you expect to see something like x minus a, some number. Here I see a plus, which means actually the center is a negative number. This one is centered at a equals -3. This almost doesn't matter at all in this problem, although you do have to keep this in mind when you get to the end. Anyway, let's do the same business, the ratio test. So here's my ale. Absolute value. All right, I'm doing n plus 1 first. Divided by 4 to the n plus 1, right? And then times the nth term in reciprocal, n x plus 3 to the n, like that. And as usual, we cancel stuff out however you can. So as far as the 4s go, I think I end with a 4 on the bottom, right? The n's, I have a n plus 1 over n, and then the x's, there's one extra s up top, so that just looks like this. You must keep the absolute value signs. It's tempting to look at that whole thing and say, isn't everything in there positive? But it's not, because x could be any real number, so this definitely could be positive, x minus 3 part, although the rest of it is all positive. What happens when we take the limit? That fraction of n's becomes 1, again, because it's a ratio of polynomials with the same degree and the coefficients are 1. So this, my L is 1/4 absolute value x minus 3. All right. And then to find the r, we set this up being less than 1. So I say 1/4 absolute value x minus 3 is less than 1. And now we don't actually want to solve for x at the end here. I'm going to multiply the 4 across, and that's where you stop. So because this is, sorry, it should be a plus 3. Yeah, I messed up the sign. I made it at some point I turned it into a x minus 3, but it's a plus 3. It's not going to matter. But anyway, this is where we stop. The radius of convergence is 4. So you should not try to like split this apart and get just x, because remember, this is an interval centered at -3. And to find the radius of that interval centered at -3, you should keep it in this form as a x minus -3. So this 4 is the R. That's the radius of convergence. Any thoughts about that one? I hope that these are, I mean, there's not a whole lot that can go wrong when you're trying these. I got one, just a quick one for you all to try, and then we'll go on to something different. How about, by the way, this is the, so if you're looking at the checklist, there are actually two things on the list about power series. The first one is called power series, parentheses, convergence. That's what this is. And then we're going to talk about something else in a moment. But anyway, power series, parentheses, convergence. I could ask you, find all x values where it converges or diverges. That's a little harder. Or I could just say find the radius of convergence. That's a little easier because you don't have to check those special endpoints. So anyway, for this one, let's just say find the radius of convergence. All right, see what you feel. Here you can use any of the tests. Although for these examples, this type of example, the ratio test is always going to be the best one. But there's certain like weird examples where you would have to use some other thing. Not good. Yeah, it's looking good. You shouldn't. You really want to keep that. So actually, this is good here? Mm-hmm. Yeah. Excellent. That's good.
Here, just get rid of the sheets. Did you also get rid of the square?
You should not get rid of the squares.
So just get rid of
You can get rid of the threes. And with the squares, I would turn it into
like the whole
big
thing square. Okay.
As a fraction square. So the 6 out of that. Just show us that my 3's on campus. All right, I'm going to try and get it going here. This is what you should be looking at, this big limit here. You got to simplify all of this business. So I'm going to see, first of all, the 3 can just straight up cancel, right? No funny business with that. The 6s, I have one extra -6 on the bottom, so this is going to have a 1 over -6 for that. For the x's, we have extra 1 on the top, so that ends up just being x minus 3. And then for the n's, I have n plus 1 squared on the top, n squared on the bottom. Now you could square those out, but it's actually easier if you collect them together like that. And then when I take this limit, that fraction inside the parentheses becomes 1 because the degrees are equal and the coefficients are the same. So this is going to turn into a 1, which means when I do this limit, I get absolute value 1 over -6 x minus 3. And you can't make the absolute values go away entirely, but you can at least do them to the 1/6. So that's the same as this. And I would say leave it like that. You may be tempted to distribute the 1/6 here, although that is not a helpful step because eventually you want to keep the x minus 3 together. So don't mess around with the x minus 3 too much. Anyway, this, I eventually end up saying this less than 1, and then I multiply the 6. X minus 3 less than 6, and so the radius of convergence is 6, right? You want to end up with x minus 3 altogether. So as part of your simplifying, don't mess up the x minus 3. All right. Any questions about any of that? Great. So this is the radius of convergence for series either centered at 0 or centered elsewhere. Let's talk. We got like 13 minutes remaining. We can discuss. The next kind of bit about power series. So that was, like I said, power series, parentheses, convergence. What I would like to talk about for a bit now, and then more next time, I will call this the power series of a function. This is something that I mentioned very briefly last time, or maybe 2 times ago, but we're going to get into this in more detail this time. Sometimes you can actually add up the series and get an answer. So some series actually sort of add up to a recognizable function. And the example that we had of that was this. This is a geometric series with a equals 1 and the ratio, the r, the common ratio equals x. And so this adds up to that. Some series actually add up to a function is what I meant to write there. I left out the a. Some series actually add up to a function. And this is the simplest example of this happening. Now this, that like equal sign there is only true when x is in the radius of convergence, which in this case is for only x in this interval, right? So that function on the right-hand side equals the series on the left-hand side for those particular values of x, and they are not equal for other values of x because the left side for other values of x is infinity, whereas the right side is not infinity, so they're not equal otherwise. But anyway, we say in this case, so we say that 1 plus x squared plus blah, 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 is the power series centered at 0 of 1 over 1 minus x. All right? It is the power series of that function. That's the language that we use. And what that means is the values of the function are the same as the values of the series as long as it's inside the radius of convergence. All right? Is the power series of that. This is also called the power series representation. And this was, if I may say something a little sort of philosophical, a very big realization that people had around the, I believe, 1700s, 1800s, when people started really talking about this. Big realization that people had is that some functions like this can be described as a power series. And this immediately got people wondering, what kinds of functions, like this function, can be written as a power series? What other kinds of functions can be written as a power series? And the surprising answer, to me this is surprising, the answer is basically all of them. Every function that you have ever heard of actually can be represented by a power series. And in that sense, to me, there's sort of a deep, this is a very deep fact, because it means something like when I was a kid, for instance, I learned about polynomials, and then I also learned about weird functions like sine and cosine or the natural log or whatever. And, you know, I can tell just by looking at my calculator, like, you have ordinary things which you get from adding and multiplying, and then you have the weird things which require a special button like sine or cosine or something like that, all right? It turns out, and this is what people began to realize when we talked about power series, even weird functions like sine and cosine, they can be expressed by power series. And so, actually, in like the universe of all mathematical functions, you have polynomials and power series, which are basically like polynomials. They go on forever. And that's it. Actually, this already expresses all of the functions that people typically talk about in mathematics. This is very interesting to me. Nobody really expected this. Everybody expected that, you know, sine and cosine are like totally different from e to the x. But it turns out actually the power series for sine and the power series of cosine actually look very similar to the power series for e to the x. Like there are sort of hidden relationships between these functions which don't seem related at all, but it turns out when you look at them as power series, there are actually relationships that you never would have expected between them. Very interesting. Anyway, what I would like to, we've only got a few more minutes, but we can start talking about this. The big question for really the rest of the semester we're going to be talking about, if I give you some other function, can you figure out what the power series for that other function is, like sine and cosine or e to the x? What's the power series of those functions? For today, we're going to talk, eventually we'll talk about some very, very sophisticated ways of answering that question. But for today, let's just talk about simple tricks. So to get other power series, something I'm always frustrated. The plural of the word series is series. It's not serieses. I feel like it should be serieses. But anyway, to get other power series, we can do simple tricks. And I'll tell you what I mean by this. So we begin with this basic fact, which we have already seen. I'm going to write this with a sigma. Unfortunately, this, if you write it in this way, you have to start the sum at n equals 0. But it looks like just x to the n, right? Starting the sum at n equals 0, you get first 1 plus x squared plus x cubed, etc. All right? So this, you just have to sort of know this formula or remember this formula. All right? That's the basic formula. And then the simple tricks involve things like, so the simple question, what's the series for 1 over 1 minus 2x? And the simple trick is you just plug it in to this formula in the box. All right? The trick is plug 2x instead of x here. All right? So if I know what 1 over 1 minus x is, if I want to know 1 over 1 minus 2x, you just do what's in the box, but you use 2x instead of x, all right? And so it says, I'm just reading what the box says, but I'm replacing x by 2x. Sum n equals 0 to infinity, 2x to the power n. Now that is not written as a power series. What I would like to see inside the sum, I want to see something times a power of x. But here I have a power of 2x. This is an easy thing to rearrange. I want to write, something times x to the n, right? What should the something be in this case? How do you simplify sort of from here to here? I want something times x to the n. Surely you all remember. What do you do with 2x to the power n? Trying to do the nth power. Anyone know what I'm talking about?
You take the ln.
No, that's way too fancy. I'm talking about simple tricks.
2 to the n x.
Yeah, 2 to the n x to the n. Is that too simple? This is maybe this. I'm not doing anything fancy here. 2 to the n x to the n, right? And now this looks like a power series. It's got some weird coefficient and then times x to the n. All right, so the power series, if you wanted to say this in words, the power series representation of 1 over 1 minus 2x is this series, 2 to the n x to the n. All right, that's kind of cute, right? Simple tricks. Basically, you have to memorize this thing in the box, which is not all that complicated, but then all other ones you can do as just a simple variation of the standard form that you remember. All right, let's just look at, I got 2 more simple tricks. How about 1 over 1 plus x, right? I don't know if anyone was bothered by the fact that the one in the box, maybe I'll copy it down just so we can still see it. The one in the box is for 1 over 1 minus x. For the sake of doing these problems, you basically should just memorize that thing in the box. But you're going to be using it so often that probably you won't have to ever sit down and memorize it. But anyway, I'm going to here, the simple trick this time would be to plug in, before I plugged in 2x instead of x, what should I do for this one? I have 1 plus x. Negative x, yeah. Let's plug in minus x here. Then it'll say 1 over 1 plus x, right, on the left side. It's 1 minus minus x, which of course is 1 over 1 plus x. And on the right side equals the sum n equals 0 to infinity minus x to the power n, which looks like minus 1 to the n, x to the n. So that is the series representation of 1 over 1 plus x instead of 1 over 1 minus x. It makes alternating signs. This somewhat weird, strange effect of changing that sign. It alternates the signs in the series. It doesn't just make every term negative, it alternates them. All right, we're going to do a bunch more like this next time. Maybe we can stop there. Please let me know if you have questions about the homework, and I'm going to go down to my office and post the grade scope assignment immediately so you can send it in. Sorry, I forgot to do that.